Hello, today we will be presenting the Dynometer Phase D presentation. Our group is composed by Michael Cavan, Abraham Andreu, Brian Perez. The agenda for today is amendments, validation objectives, system level MOPs, validation procedures, project plan, and system budget. Since the beginning of the project, the main MOP has been the cost. In our Phase A presentation, the cost was estimated to be $8,000. However, when we reached Phase C1, with all the calculations and research done, the project had an estimated cost of $14,000, which we exceed by $6,000 original budget. For the reason of surpassing the budget, we decided to make an amendment and reduce the parameters and cost greatly. The parameters that will be changed will be roller dimensions such as length and diameter, the size of the brake calipers, brake disc, and the chassis. With all that in mind, we also are going to test the dynamometer for a smaller vehicle that will have a smaller velocity and smaller horsepower.
For the roller calculations, the vehicle speed was modified to 15 miles per hour. The roller diameter was changed to 3 inches and the engine RPM to 1600 RPM. The vehicle horsepower will be 0.05 horsepower and the total time for the pass will be 5 seconds. This results in a maximum RPM for the roller of 1679 RPMs. With the amendment, the inertia will now be 0.807 pounds per foot squared, and the roller weight calculation, the material used now will be aluminum that has a density of 2710 kilograms over meters cubed. This results in a total weight for the roller of 8.3 pounds.
For the amendment of the chassis, the dimensions will change because the force applied by the vehicle and all of the components will be much less than the 3,000 that was originally stated for the project. The new force to be applied will be 50 pounds. With that in mind, changing 50 pounds in all of the equations, we have a new minimum cross-sectional area of 0.06 square inches. Once the research was done, the available material smallest cross-sectional area was calculated to be 0.08, which exceeds by 0.02 the minimum required. This new dimension for the tubing will reduce cost.
Okay, so for the amendment that was done to validate the system, the main changes in this subsystem case is going to be the roller inertia is going to be 0.807 pounds per foot squared. Time to stop is going to be the same at 10 seconds. Pad friction coefficient is going to be the same because the pads are the same material. The roller speed is going to be slower. The acceleration needed is going to be lower because of that. The torque needed to stop is going to be lower too. The pad dimensions are going to be smaller, and the piston diameter is going to be a lot smaller. This is because we're basically doing everything in scale, which is going to lower all the numbers. As you can see, using the same formulas we used in phase C1 with the new numbers gives us a hydraulic line pressure of approximately 687.683 psi and a safety factor of around 1.89, which is well in the limit that we set at first in the MOPs. Now for time to stop, using the same data that we used in the last slide, we had to bump the line pressure up to 700 psi in order to get the braking time under 10 seconds, which in this case is going to be 9.824. Again, we are using the same pad material, so the pad friction coefficient is going to be the same. The pad dimensions are going to be way smaller because it's a scale system, and the roller inertia is going to be smaller because the roller itself is a lot smaller.
Now for the last calculations made for our amendment are for the emergency brake system, which is subsystem number 4. The specifications that changed were the inertia of the roller, which is significantly lower, the diameter of the disc, which is D0, originally it was 15 inches, now it's 6.69 inches. The friction of the pad, of the brake pad, which is now 0.36, originally 0.31. This changed because now the brake pad is going to be a normal steel one because ceramic pads do not come for the dimensions needed for this new brake system. The diameter of the caliper's piston is significantly smaller because the brake system is smaller, so the caliper is smaller, the brake pad is smaller, which also explains why the angle between zeta 2 and zeta 1 is also smaller. The angular velocity of the roller also changed. Used to be about 300 radian per second, more or less. Now is 175.85 radian per second. With these specifications, all calculations below changed. The important ones are the angular acceleration, which uses the time in which we need the emergency brake system to stop the roller, the brake torque, and most importantly, the hydraulic pressure. As as it has always been said, it cannot surpass the 1300 psi. Here we can see it's around 879 psi, which gives us a safety factor of 1.478, which is a pretty good safety factor. At the end, we can see the calculations to see if the roller will actually stop in 4 seconds. And yes, with this calculation, we can conclude that yes, it will stop in 4 seconds. The validation objective for the dynamometer is to design and develop a dyno prototype at a smaller scale to validate the analysis and calculations completed, considering a future development of full-scale dynamometer. This is to optimize the safety of students handling the car while at the same time reducing time and money consumption of buying a dynamometer.
For the verification and compliance, we have the MOPs, which are the roller length shall be between 8 and 16 inches. The roller must withstand the vehicle speed of 15 miles per hour. The roller must withstand a maximum power of 1 horsepower. The chassis must withstand a maximum weight of 50 pounds. The main brake system shall stop the dyno in 10 seconds. All hydraulic lines shall not exceed 1300 psi. The emergency brake system shall stop the dyno in 4 seconds, and the chassis cannot crack nor bend the project vehicle on top. We will be using different tests used to verify all these MOPs with validations or verifications, and there will be a series of different experiments where this will be validated. Validation procedures. Experiment number 1, roller and chassis validation. Roller and chassis validation. For the following objectives, including that the roller length shall be between 8 and 16 inches of length, the chassis must withstand the maximum weight of 50 pounds, and that the chassis cannot crack nor bend with a project vehicle on top, will include an equipment and experimental setup, including the dynamometer, a measuring tape, and different weights. For the safety precautions, we should always use safety goggles. Non-operators shall remain distant from the dyno, should not wear loose clothes nor jewelry, including watch, bracelets, and/or chains. And if you have long hair, this must be tied up. For the measurement experimental procedure, first we will secure the dynamometer on an even and firm surface. The dynamometer will remain in this position during the experiment. Then we will measure the roller and take note of this length. We will weigh the project car and take note. Then we will measure each weight separately and take note of each measurement. Stop taking measurements once there is a sum equal to 150% of the total weight of the project car. For example, if the project car weighs 10 pounds, there should be a total sum of 15 pounds. Then we will place one weight on the chassis and inspect for cracks and bending. If there is no noticeable deformation, repeat until step 5 until all weights are on top of the chassis. For the data collection, we will be using the following table for all measurements. That will include all measurements completed with each one of the weights in pounds.
So now we're going to be going over the validation procedures for the second experiment, which is going to be the main brake system validation. For the main brake system validation, we're going to have first our objectives, which is that the roller must withstand a vehicle speed of 15 miles per hour and a maximum of 1 horsepower. The main braking system shall stop dyno in 10 seconds or less. Our hydraulic line pressure shall not exceed 1300 psi. Equipment and experimental setup. We're going to need the dynamometer. We're going to need a project vehicle. We're going to need a pressure gauge, a stopwatch, and an RPM sensor. For safety precautions, we're going to have to use safety goggles, where the non-operators, the people are just standing by, like the person that's going to be recording, they have to be distant from the dyno. We never want to put our hands close to the roller or the vehicle wheels during a pass, and we do not want to wear loose clothes or jewelry that might get stuck on the dyno itself. As for experimental procedure, for this experiment we're going to have to install the sensor on the wheel or axle of the project vehicle. This sensor is going to measure our RPM. The location of it is going to depend on the convenience for the user, so it depends on which vehicle we're going to end up using. The pressure gauge has to be installed between the actuator and the brake for the main braking system. This is going to give us our hydraulic line pressure reading. We need to place the project vehicle's rear wheels on the roller for the dynamometer. We have to secure the vehicle in place so that it doesn't move during the experiment. Release the main brake system by lowering the actuator. We have to accelerate the vehicle for 10 seconds. This is going to be called a pass. During the pass, we are going to take note of the maximum RPM produced by the vehicle. It's going to be used later for our calculations. Now after that we want to pull the lever of the main brake system and start the stopwatch. With the actuator in use, take note of the pressure reading on the pressure gauge. Stop the stopwatch once the roller's rotational motion comes to an end, and take note of this time. Finally, for this experiment, this is going to be the table we're going to be using to collect data. Basically, we're going to have vehicle velocity in RPMs. This is going to be our wheel speed from the RPM sensor. We're going to have our braking time, which is going to be the time that's going to be measured by the stopwatch. Our oil pressure in PSI is going to be our hydraulic line pressure. The vehicle velocity in RPM, braking time, and oil pressure, we're going to take these twice and then average them so that we can have a final result.
Our validation procedures concludes with experiment number 3, which is the emergency brake system validation. Now for experiment number 3, the objectives are the roller must withstand a vehicle speed of 50 miles per hour and a maximum of 1 horsepower. The emergency brake system shall stop the dyno in 4 seconds or less, and the hydraulic lines shall not exceed 1300 psi. The equipment that we're going to use for this experiment are the dynamometer, the project vehicle, a pressure gauge, a stopwatch, and an RPM sensor. The safety precautions that are needed to make this experiment are always use safety goggles, non-operators shall remain distant from the dyno, never put hands close to the roller or vehicle's wheels during the pass, and don't wear loose clothes nor jewelry. The experimental procedure for experiment number 3 is step 1, install a pressure gauge between the actuator and the brake for the emergency brake system. Step 2, place the project vehicle's rear wheels on the dynamometer roller. Secure the vehicle in place so that it does not move during the experiment. Step 3, release the main brake by lowering the actuator. Step 4, accelerate the vehicle for 10 seconds. This is called a pass. During the pass, take note of the maximum RPM produced by the vehicle. It will later be used. Step 5, pull the lever for the emergency brake system and start the stopwatch. Press excuse me. Step 6, with the actuator in use, take note of the pressure reading on the pressure gauge. And the last step, step 7, stop the stopwatch once the roller's rotational motion comes to an end. Take note of this time. This is the table we're going to use for the data collection of experiment number 3. As one can notice, there is basically two of each data collected, which are the vehicle velocity in RPM, the braking time in seconds, and the oil pressure and PSI. The reason why you should take two data for each for each is that way you can do an average and have a more precise data.
For the project plan, we have the last 2 weeks of February and the first week of March, the parts ordering and manufacturing process. The second and third week of March, we will be doing the dynamometer assembly. And the last week of March, we will be completing the system validation. For the month of April, we'll be completing the overall project conclusions, the overall project recommendations, the book writing, and the poster making. These will be the final steps for completing our Phase F presentations on April 30th, 2020.
The system budget changes drastically from the $14,000 that is expected from the project on a full scale. Right now, most of the cost is going to go to the fabrication of the chassis component, that being $104.78. The two brake systems are $60.83 for the main brake and $65.78 for the e-brake. Finally, the roller is $69.98. Pero estabas allá peleando con Fabiola y no puedo grabar con... The total cost for the project will be of $301.37.